Hello and welcome everyone to the DS3 Developing Secure Systems Summit panel on fuzzing. It is my great pleasure to welcome all of you for an exciting evening, morning, night, afternoon, or wherever you are. It's an interesting coincidence that we're going to bridge across many different time zones here. I'm Matthias Peyer from Europe. I do run the HexHive group here at EPFL in Lausanne, beautiful Switzerland, where we focus on all forms of finding, fixing, and mitigating bugs. And yeah, it's my great pleasure to moderate this panel here, where we have 3 world experts on all aspects of fuzzing. We'll have Marcel from beautiful Australia, Kostya from Google, beautiful California, and Justin from, I think, Washington State. Let me start with a little bit of logistics. Our panelists will all start with a 10 to 15 minute position statement where they are going to talk about some of their background, and then we'll dive into a set of fun discussion topics for the first half of the Q&A sessions. And then we're going to focus on questions from the audience as well. So as you all know, panels really live through interactions with the audience. And please do write the different questions in a chat, as YouTube comments, through Twitter, send them through email, or send us a carrier pigeon to whoever is closest to your geographical region. Next slide, please. The first panelist is Marcel Boehme. He's currently at Monash University, and he will soon move to MPI for security and privacy in Boehme, back to Germany. He did a PhD at NUS with Abig Roichuduri, who finished in 2014, who's also well known in software engineering, where he already started and led a lot of his groundwork on fuzzing. He then did a postdoc with Andreas Seller, who just came out with the Fuzzing book in Saarbrücken, and he will present us some of the academic perspective of fuzzing and dive into some of these core topics here. Next slide, please. The next speaker will have Kostya Serebryany, who is fairly well known through the tools that we use all in our daily life, address sanitizer and threat sanitizer. He has been at Google for a pretty long time, I think since 2007. Before that, he was at the Sun compiler group and Intel compiler groups. He told me that he did a PhD in ancient history in Moscow, and I would consider him a part-time academic, but full-time engineer. So he makes sure that his stuff actually works in practice. And last but not least, next slide, please, we'll have Justin Campbell, who's running or working for Microsoft Platform Security, focusing on operating system security. And he seems to be one of the person that is really looking out for privacy, as he's really, really hard to find on the internet. And he will be our principal engineer focusing on that. With this short introduction, we'll move on to our panelists. You don't want to hear me speak, you want to hear the panelists speak. So we'll start with Marcel Boehme. Please start writing your questions in the chat so we can use them after the position statements. Marcel, please take over the floor. Thank you.
Thanks, Matthias, and thanks for the invitation. And I'm really happy to be here and discuss fuzzing with everyone. And let me share my screen first. All right, so who am I? My name is Marcel Boehme. I'm an ARC DECRA fellow and a senior lecturer here at Monash University. And my focus is on fuzzing. And so fuzzing is about making machines attack other machines. Why is that important? Because lots of our infrastructure is actually based on small little components that are widely spread, like on very critical infrastructure like the internet. So if you're using a browser, for instance, there's a component called OpenSSL, which talks securely, which makes any two components on the internet talk securely. And if you find a bug in OpenSSL, which is this very small library, suddenly a lot of machines are vulnerable to attacks. And so it's important to find bugs in programs. And there are large efforts and lots of I'm really looking forward to hearing what's happening in industry at Microsoft and Google to make fuzzing a reality and use the power of fuzzing to find bugs in industrial scale software systems. So my focus in this is research in how to find bugs as fast as possible, that's efficiency, how to find a maximum number of bugs, that's effectiveness, and how to find bugs in programs of arbitrary scale and across arbitrarily many machines, so that's scalability. And I'm particularly interested in not only coming up with these techniques, but also in the foundations of these techniques. What are fundamental limitations of existing techniques? And I'm going to show a couple of those limitations in a second. But before I do that, let me just show you, give you a very short introduction on what fuzzing is. So in the very simplest case, you can consider a program as a black box. So a program takes inputs, and if you're interested in certain behaviors of the program, then you have detectors. Like suppose you're interested in security flaws, you have a detector of a security flaw, like an address sanitizer or some other sanitizers that would flag a security flaw, like a memory safety issue, once you generate an input that it exposes a memory safety issue. So now the objective of a fuzzer is to generate those inputs such that, for instance, address sanitizer would raise a crash. So you can generate these inputs by you're using a random stream of bytes, or you could, if you have information on the file format, generate inputs according to that file format. Or if you have files lying around, you can just mutate those files. That's called mutational fuzzing. And so fuzzing is very simple in that sense. You just have a black box, you generate inputs, and you try to find crashes. So then there is a white box fuzzing, which is you consider a program as a white box. So you want to you have information on the structure of the program, like an if statement, like if a less than 0, then a white box fuzzer would be able to go along both paths of that if statement, setting a less than 0 and setting a greater than 0. So, but because you have this, so then you can collect these branch conditions, compute a path condition, negate a branch condition, and pass that to a constraint solver. There's a lot of machinery behind white box fuzzing, which makes it a little bit slower. But in principle, it's very effective. You can find all the bugs with symbolic execution with white box fuzzing. For instance, if you have address sanitizer, say, if area index is greater than the size of the array, you could have a white box fuzzer go along that path too. So symbolic execution is very effective, but a bit slow. So gray box fuzzing kind of solves this problem. You still have like 10 to 20,000 executions per second, like a black box fuzzer, but you can also somehow enumerate paths. So a gray box fuzzer works like that. You generate an input by mutating a seed, and if that generated input increases coverage, for instance, exercises a new path, then you add it to the seed corpus.
Let's give him another second to connect back. Otherwise, we'll move on. He seems to be having internet connectivity issues. Maybe somebody drove into or cut the internet cable. I think you're back, Marcel. Cool.
Okay. All right, so that's the internet in Australia. And so if you're, if you now consider this very fast execution in black box fuzzing, right? You can generate 10 to 20,000 executions per second in black fuzzing. And box fuzzing being this very effective technique that can find all the bugs. In practice, white box fuzzing doesn't really find a lot of application because it still finds less bugs than a black box fuzzer or a gray box fuzzer. And the reason is, and that's been known since the 1980s, and the reason is because there's all this machinery, and in that time that a white box fuzzer generates like 10 inputs, a black box fuzzer has already generated maybe 1 million inputs. So for instance, if you take AFL now, which is a very efficient gray box fuzzer, and you make it a little bit smarter, it becomes very difficult to kind of that you spend more time doing program analysis and less time generating more test cases, and you might even make it worse, even though you make AFL smarter. So efficiency is very important in fuzzing. So another limitation, so that's what's a fundamental limitation of white box fuzzing. You have to be fast enough. And here's a fundamental limitation of black box fuzzing or gray box fuzzing. So the insight in scalability is if you have an exponential number of machines and a given time budget, you increase the number of machines exponentially, you'll only find a linear number of new bugs. So suppose you find 10 bugs on one machine, you double the number of machines, you might find one more new bug in 24 hours. Now, if you double the number of machines again, you might only find 2 more bugs, so 12 bugs in total. So as you increase the number of machines exponentially, and that's an empirical finding, you might only find a linear number of new bugs. So that's an interesting, another limitation of black box fuzzing. So now, okay, so now we know that fuzzing comes at an exponential cost. So why do fuzzing at all? So now suppose we have OSS fuzz and we've run 10 or like 100,000 machines on the same programs over and over again. Does it make sense to continue fuzzing? And because, do we find new bugs? And the answer is yes, because these systems are being continuously developed, and during the continuous development, people are introducing bugs. And as we found, they're introducing bugs at a constant rate. So you run OSS fuzz, this is data from OSS fuzz, as you run continuously, as you run the fuzzer continuously on the newest version of an operating system, you find bugs at a constant rate of about 3 to 4 bugs per week. So you need to run fuzzing continuously. And another part of my research is about when to stop fuzzing. So the question is, fuzzing is not verification, so we can't prove the absence of errors, but at least we can quantify to some extent what the probability is of finding an error after having run the fuzzer for some time. And if the probability of finding a new error drops below a certain allowable threshold, you could stop the fuzzer. But this is ongoing research. So that's some research that I've been doing. Now over to Kostya.
Hello, everyone. Here are my slides. My name is Kostya Serebryany, and next slide, please. I have been with Google for more than 13 years. Most of it I was first creating and then leading a tool called Dynamic Tools. Almost 10 years we've built a tool called Address Sanitizer, which quite a few of you know. We've built other sanitizers, Thread Sanitizer, Memory Sanitizer. We've built LibFuzzer, one of the popular fuzzing engines nowadays. It is part of the LVM toolchain. We've built Sanitizer Coverage. It's a compiler pass that is used by several fuzzing engines to collect coverage. After the hard bleed in 2014, we realized that, okay, we have those fuzzing tools, but nobody's using them because there is no infrastructure. And we initiated OSS Fuzz, which is currently the largest service for running fuzzers, at least for open source. We spent quite a bit of time and effort on what we call structure-aware fuzzing, where the input is a highly structured thing. We typically deal with protobufers. This is a serialization, deserialization layer for most of the Google applications. We have built an open source tool called libprotobuf mutator, which allows you to plug structure-aware fuzzing into libfuzzer easily. I'm also indirectly involved with a number of other fuzzing efforts. Syscaller, the kernel fuzzer, and GoFuzz, a fuzzer for the Go language, are built by my teammates. And FuzzBench, a benchmarking system for fuzzing engines is built by sister team. My involvement in FuzzBench was that I was asking for it for a few years. And recently, for about a year and a half, one of my team is specializing on a fuzzing engines for some specific proprietary targets. One specific proprietary target. We're also doing things that are not directly related to fuzzing. GWIP-SN is our tool for sampling-based error detection in production. We have deployed it in all of our ecosystems, more or less. Hardware memory tagging, think of it as address sanitizer in hardware, is one of my major topics nowadays. And finally, we're working on dynamic data flow analysis, or taint tracking. And so far, this is unrelated to fuzzing completely. Next slide, please. So I spent a good couple of years working on LibFuzzer and tuning its performance and efficiency. And this work is just completely amazing and fascinating to me. It's very interesting. But a couple of years ago, I stopped working on it actively, in part or maybe primarily because fuzzing engines are not the weakest link in the whole chain of program correctness anymore. And let me give you an example from another area. So syscaller, which I mentioned, is a guided fuzzing engine for Linux kernel and other kernels. And it had almost no major algorithmic changes for a couple of years now, probably. And still, we're getting large gains in bug coverage due to basically scaling. So we run on more machines. We cover more parts of the Linux kernel and other kernels by just writing the syscaller descriptions and so on. So for syscaller and for many other areas, the quality of the fuzzing engine is not the blocker, is not the weakest link anymore. It is definitely not true in many particular cases. Like if you have a library that has been fuzzed for many years, which has close to 100% code coverage from the fuzzing corpus, then anybody who comes with a stronger fuzzing engine will find some extra bugs. But in general, if you look at Google scale, fuzzing engines are not blocking us anymore. And let me describe what I think are the weakest links that we need to address first. First of all, creating and maintaining fuzz targets remains to be not as easy as I would like them to be. And I would like them to be as easy as creating unit tests and frameworks such as gtest. Hopefully even simpler, because gtest is a library written in C++, and some more modern languages have gtest-like capabilities included into the language, and I would like the same to be true for fuzzing. Next important topic is structure-aware by default. Currently, many fuzz targets are treating the inputs as bags of bytes still, and only with some extra effort they become structure-aware, where the fuzzing engine knows about the structure of serialized input. For it to be the default, we actually need to write our code differently, so that most of our code components are things like proto-in, proto-out, or thrift-in, thrift-out, whatever is your serialization layer. It will also simplify fuzz target auto-discovery, which is an important topic, but for arbitrary fuzz targets, like when our fuzz target consumes a bag of bytes, it's really complicated. And in general, for software engineering practice, it's a good idea to structure your code such that every component takes some kind of standardized input and produces standardized output. Another important point that most of the ecosystems I'm involved lack to some extent is coverage monitoring with a human in the loop. What I mean by this is that we not only need to provide users with the code coverage metrics and visualization, but we also need to explain to the user why certain things are not covered and what the user can do to cover those things. Next, we really need to tie testing and fuzzing with production much closer. And for that, we need to build feedback loops from production telemetry back to testing. For example, we need to be able to compare the code coverage achieved on production binaries with that of testing and fuzzing. We want to be able to explain why a given production crash was not discovered by fuzzing. And we need to fix this. And we need to fix all of those cases until the time that all the production crashes are discoverable by fuzzing. And then, in theory, we'll not have any production crashes anymore. One of the major pains I have is collecting inputs from production for fuzzing. So suppose you have a large production system that gets inputs from users, and users are the ultimate fuzzer. But it is very hard and sometimes impossible to use these inputs for the fuzzing purposes, sometimes for privacy, sometimes for some logistical reasons. So these are the things I want to build and improve before I get back to developing fuzzing engines. Next slide. Yet I still want to get back to developing fuzzing engines because it is fascinating, it is algorithmically challenging. And I do believe that there will be quite a few breakthroughs in the coming years. So if and when I get back to developing LeapFuzzer version 2, maybe, I would focus on 4 major areas. So first of all today's fuzzing engines that use coverage guided approach, they have the problem of corpus expansion. You don't want a very large corpus because it will be too expensive and too slow. You don't want too small corpus because it will lose quality. You want some middle ground, and you want the best possible oracle, which tells you when to add an element to the corpus, when to evict an element to the corpus. And we typically use combined coverage maximization as an oracle. We need a better oracle. Maybe it will be coverage distance maximization, maybe something else. We need metrics better than coverage, and this is something we need to invent. I don't have anything to offer yet. We need smarter mutations, and by that I mean the mutations that touch only those fields, and I hope we'll have structure-aware fuzzing everywhere, so this will be fields in a protobuffer or thrift or whatever, not arbitrary bytes. But we still need to know which fields to mutate if we want to affect an interesting branch in the code. Finally, I think we need to put more focus on differential fuzzing, even in those cases where there is no second fuzz target to fuzz and to do differential testing against. Like we can do differential testing against different builds of the same fuzz targets, or different revisions, or some other flavors of the same code, simply because differential fuzzing gives us extra extra feedback for corpus growth. And of course, when we can use differential fuzzing for two different targets, it's very powerful. That's it. Thank you.
Thank you, Kostya, for the statement. And sorry for dropping out before. My laptop overheated thanks to Microsoft Teams. Maybe it was fuzzing in the background, so you shouldn't do that on a production machine. Thank you for your statement. I think there's a lot of interesting topics on here that we can pick up in the Q&A, in the panel discussion afterwards. But let's hear it from Justin as well, so that we can get his statement from the also practical engineering side as well. Justin, are you here?
Yep.
Cool. So why don't you take it over?
Great. My slides come through.
Yep. See them all.
Great. Yeah. So I'm Justin Campbell. I'm from Microsoft Platform Security. You can think of platform security as operating system security team. The largest product that you probably know us from is Windows. My team and I have also been involved with fuzzing specifically around OneFuzz, which is the open source platform, makes it possible to fuzz at scale using Azure. You probably know our team from a number of noteworthy bugs that other people have named for us, sorry, like SMB Ghost, Deja Blue, Bad Neighbor, a number of other unnamed kind of highly critical issues that have existed for a period of time in Windows before we were able to make the investment to go and ferret out those things in older code. We also work on developer tools for software safety and compiler and exploit mitigations as well. So I just want to start by framing a little bit on the scale of the problem that our team is tackling. And so obviously, Kostya, Google, referring to Google scale, Microsoft and Windows as well, kind of in the same realm, but I thought I'd put some numbers around it. Windows itself is 5.7 million source code files, 5.75 million. Obviously, when we think about like average file size, we're talking about the hundreds of millions or billions of lines of source. 1,100 PRs a day, all of those automatically reviewed with static analysis, in addition to the fuzzing stuff that we'll talk about today. 3,600 developers pushing those PRs every day, and 440 official branches. And in Windows, an official branch is just one that gets a nightly build where you can get media, install it, run it, set up an interesting configuration. And the thing about Windows that isn't automatically intuitive to somebody outside the company is it's actually a very large family of products. You have client and server and IoT, and large parts of Windows go into the Azure host, et cetera. So it's not one big team, it's many teams cross-contributing to many features across many branches, contributing to many dozens of different product lines. In addition to all of the internal work, we also pay very close attention to external reports that are submitted to the Microsoft Security Response Center, or MSRC. And we spent a lot of time digging in on why our existing methods didn't catch those and look for themes and opportunities to improve, whether that's in fuzzing or in static analysis. But I think fuzzing is definitely our bread and butter for finding issues at scale. And it's always very interesting to us when somebody reports a bug that we didn't catch. And so to that end, we think fuzzing can do a lot more. I think some concrete opportunities here are domain-specific sanitizers. So in the same way that we might think about writing a static analysis checker for a pattern of issues that we've spotted, we'll also introduce domain-specific sanitizers or checkers that run at runtime during fuzzing. And so things like that might be path or redirection issues, or improper handling of tokens and impersonation, things that are just really easy to get wrong and lead to really high volumes of issues. And in this way, we really treat fuzzing as automatic test generation, similar to differential fuzzing. So we're really just using the fuzzer to maximize code coverage and exercising as much code as possible while we're performing these runtime checks. And we can tap into this same approach to help enumerate what's on the attack surface. So static data flow analysis, runtime data flow analysis can help us get there, but there's really no substitute for the amazing power of that gray box coverage guided fuzzing for automatically ferreting out things that wouldn't necessarily have been apparent statically. And on top of that, we can also expand our idea of what coverage means beyond topology. And I'm really hoping to dig into this a little bit in the panel portion, but we've had some really big breakthroughs on like enabling security researchers and hackers to more greatly express the possible state space that a program can enter, and making sure that we're letting the power of coverage guided fuzzing help us get there. So, and when we think about like the utility of fuzzers and the kind of like ways in which we can employ them creatively beyond just ferreting out memory safety, I've picked up an example, and hopefully this font is big enough. This is a snippet from a GitHub PR where they have added fuzzing support to their open source project. And so this is a Microsoft employee working on an open source product. And you can see what they've done here is used fuzzing as a magic input generator. And if you go and read beyond the box a little bit, what they've done is in their investigation for picking up code that they didn't write, or that they are legacy code that they're required to maintain, they're using fuzzing as an automatic exploration tool where they can set a breakpoint and wait for the breakpoint to hit, and then go look at the input that got them there, and then they can begin to reason about what type of input this code was meant to handle, and then they can perform dynamic analysis, interactive debugging, et cetera, kind of ferret out like what the code is meant to do. And like any good technology, it's indistinguishable from magic for its user. So in this way, we can see that like when we make something as powerful as fuzzing as accessible as it has become in some scenarios, developers will find emergent uses for it, and it becomes an extremely powerful tool in their toolbox. So one key insight there, though, is if we're thinking about making things accessible and we're thinking about the power and utility of fuzzing, hacker fuzzing is different than developer fuzzing. And I don't know how common of a line of thinking this is, but this is definitely the way I and a lot of my team think about this. Hacker fuzzing is composable, it's powerful, and typically very interactive, right? A security researcher or hacker is guiding their fuzzer in, or taking feedback, or crafting inputs to maximize coverage, et cetera. There's obviously tremendous room for growth remaining in that hacker fuzzing domain. Developer fuzzing is where we meet software engineers where they are, and when fuzzing works in a way and has interfaces that are intuitive to them. Kostya had mentioned libfuzzer and syscaller, and those are both an amazing start. But what else can we bring from the world of hacker fuzzing into developer fuzzing? And how can we make it even more accessible, right? How do we make it as intuitive as a unit test? How do we make things like feedback actionable for developers in the same way that sanitizers, whatever domain they're in, ensure that we get actionable bug reports out of our fuzzing? So fuzzing is obviously an incredibly valuable quality signal. Unfortunately, though, security teams often want to find the bug, maybe submit a fix, maybe verify a fix the development team submits, and then move on. However, as you heard Marcel mention, it's not verifiable, right? And so we know we can't durably secure systems exclusively with fuzzing. And so the way I've been thinking about this recently is that if you find one bug, if you're a developer, you've written a fuzzer, you run it, and it finds one bug, an excellent next step is to go and fix that bug. If it finds 20 bugs, it's time to rethink how that component is written. There are a number of tools or a number of different approaches, but really what this is saying is if you fuzzed out 20, it's very likely that there's a 21st waiting to be found for somebody with that better or more novel engine, or someone who's willing to put in the work to go find the kind of bug that a fuzzer isn't likely to find. And so making systems easier to get right or harder to get wrong whether that's in re-architecting for simplicity or legibility or testability, or applying a number of durable solutions to solving the same problem. All of those are kind of in scope, and that's a big part of what my team focused on. Specifically, we want to be thinking about durable solutions. So of course we want to be fuzzing, we want to be testing at every build, but we also want to make sure that teams are using tools, languages, libraries that are hard to get wrong. And so I've got a variety of projects here, but Project Everest is a formally verified C code generator. There was a blog this week about the work that Microsoft Research has done in conjunction with the networking team, with some small collaboration from my team, to introduce formally verified packet parsing into the Windows parsing stack, the network parsing stack, specifically to help with security in both Azure and in Windows Client and Windows Server. Rust is a kind of the go-to recommendation these days. We want to see more components written in Rust. We want to see old problematic components rewritten in Rust. And then when you absolutely must keep your hand-rolled C, C++ for a variety of reasons, there are safer libraries, things like GSL and a whole host of others out there that are available that teams can pick up and, again, kind of make it tough to get things wrong. One of the great things about all of these approaches, though, is our fuzzers and sanitizers still work just fine, even if we've rewritten everything using one of these safer approaches. And so in the corner cases where things are unsafe, or for properties that these systems can't verify, we can still use fuzzing to detect where there might be gaps or omissions. And I wanted to keep it a little bit brief to make sure we had plenty of time for the discussion. And that's all I had on my kind of opening statements.
Awesome. Thank you very much, Justin. And thanks to all of the panelists for their introduction statements. Yeah, now we can actually see the panelists. This is super cool. We're going to move over to the interactive part. And I prepared a couple of questions to get us all started, but this is also an opportunity for the audience to join in. So do send us your questions. We have people looking at the YouTube stream. We have I'm looking at the chat here in Microsoft Teams as long as I'm online, and we do have people monitoring Twitter or whatnot. So please send us the questions in any way possible. But let's start with a couple of questions that came up as part of your positioning statements, initial statements. And I want to follow up on something in between Kostya and Justin first. So both of you talked a little bit about the continuous integration and fuzzing as part of a larger ecosystem. And let's just say Microsoft and Google may be at a different position than your average company. How do we get these kind of tools into a company that is not running at the scale of Microsoft or Google? And how can we make fuzzing more accessible and turn this into a more common approach for developers? How can we teach it better? How can we inform developers? How can we give them the resources and so on? Who wants to start? Who wants to take the question first? Sure, go ahead, Justin.
Oh no, I was saying, go ahead, Kostya.
Integrate fuzzing with GitHub.
That's the easy answer.
This will instantly give all the open source people and all the people who use GitHub for the closed source things, and it will motivate every other ecosystem to follow.
Yeah, I strongly agree, and it's actually a great specific tech call out. The integration of CodeQL and static analysis and making it as simple as a single click has greatly sped the adoption of static analysis, and everybody kind of immediately gets the benefit in the ecosystem. If we could do that exact same thing for dynamic analysis, obviously there's a whole host of technological challenges there, making sure you've got the same kind of standardized interface. But I think there are de facto standard things that you could start with libfuzzer being a great example. And I think we've actually done some lightweight integration with GitHub in OneFuzz. It's definitely not, at the level it would need to be to kind of drive this mass adoption that Kostya is referencing there. But I think we think very alike on that one. If you make it ridiculously simple for the place where people already are, you meet developers in the way they work, the rest kind of just follows automatically.
Yep. Makes sense. Marcel, how do we teach fuzzing?
So fuzzing is not really. So maybe I just want to answer the also follow up on what Justin and Kostya said. So fuzzing is really simple for industry to adopt. So AFL really requires only a command line interface. So anything that reads a file, AFL is just generating that file and then just collects coverage feedback. So you have to. It's really easy to integrate into the compiling infrastructure. So you just compile your program instead of a normal GCC or Clang. You compile it with AFL GCC or AFL Clang Fast, and there you get your coverage feedback. And then you just point the fuzzer to your program. libfuzzer takes a little bit of it's a bigger step. So libfuzzer allows you to consider your program as a unit. Libfuzzer is more like a unit testing fuzzer. So you can write your fuzzer harness and point your fuzzer harness to the function that you want to test, the unit that you want to test, and then you run libfuzzer, and it's really easy because libfuzzer is integrated into LLVM, which is the compile infrastructure. So it's really easy to start fuzzing as an industry, as a company. There are lots of tutorials out.
How do we get the developers to actually use fuzzing? Right. So how many people at Microsoft or Google do write fuzzing test cases? There's not. There's enough, but there's not that many. How many are there in other public companies, right? Like you still need people to write these libfuzzer tests to get them started. Libfuzzer is great. It requires some developer effort though, and a different style of thinking. How do we get there?
So there's another perspective, which is the open source perspective. So if you're an open source developer, there's a lot of incentive that is particularly put by Google for open source developers and other people to make fuzzing available to critical open source projects. There's this project called OSS Fuzz, which is this entire infrastructure. You just submit a fuzz driver, test harness, and essentially connect the fuzzer to the open source software. And you'll even be paid for that. You don't need to be the open source developer, but still the open source software will be made fuzzable. So yes, fuzzing still requires a little bit of effort, and we have to, as Kostya said in his talk, we have to get it to some point where fuzzing is transparent in some sense. You just say this function needs to be fuzzed, and the test harness should be created in the background, and the fuzzer should automatically test that function, set up the context, and fuzz that function. That's where we should get. That's where we are not yet. But yes, industry is getting very interested in. I mean, if you just have the objective of finding lots of bugs in your programs, because there are a lot of vulnerabilities possible, right? Then you should also get familiar with fuzzing. And as I said, there are a lot of efforts now, both in the academic community as well as in the industry, to make fuzzing more user-friendly. So now to your question, how to teach fuzzing. We have this, so I'm a co-author of this book called Fuzzing Book. It's like a tutorial. It's like a Python tutorial. You can go through that tutorial and start with very simple black box fuzzing approaches, go all the way to symbol execution. So I've been using that in my own teaching, and Andreas Zeller, who's the main author, also has used this in his teaching.
Cool. Yep, it's definitely highly recommended. You start in Python and then you go down to a real language. Kostya, you wanted to follow up as well.
Yeah, with regard to how do we get more people to fuzz, I have an idea which had very moderate success, or I would say very little success, but still I think there is something. I call it regression fuzzing. Whenever your organization or whatever hits a bug of some specific severity, your developers have to introduce a fuzz target or a fuzzing process that would rediscover this bug when the fix isn't unpatched. Well, just a handful of successful stories like this, where a fuzz target introduced like this would find more bugs in the same code. We need more of this. And this is very similar to regression testing. In the same way, 15 years ago, the concept of regression testing was almost like alien to many developers I worked with. Now regression testing is, of course, you have to write regression tests.
Yep, absolutely agree. Justin?
Yeah, I just want to echo that. It's funny that I think we landed on the same term, maybe independently, that we call it regression fuzzing. When you hit a bug, if you don't have a fuzzing harness that would have hit the bug, it's time to write a harness. And if you do, it's time to introduce an input. And we've actually seen a fair number of things. As people are fixing the second, third, fourth bug, they accidentally reintroduce something that smells just like the first one, and the system catches it and saves them from themselves. So yeah, definitely like super successful, super powerful paradigm. I imagine there's more wisdom we can draw from general testing into the fuzzing realm in the same way that particular insight was.
Right. I think that makes a lot of sense. I want to go back to your more than 20 bugs statement that you made in the opening statement, but we're going to get there in a bit. I want to go top down, right? Many of you mentioned numbers of bugs found and bugs discovered. And I do remember one of Kostya's earlier talks where he talked about that many thousand bugs in Chrome, that many thousand bugs in Google internal code. There were talks from Microsoft about thousands of bugs found. If you look at some of the recent syscaller queues, I think I checked it this morning, there were like 940 crashes that were not assigned or not open issues in the Linux kernel that were discovered. Are we not having too many bugs at the moment, or what's the issue here? How do we go from crashes to bugs? How can we get meaningful information out of the fuzzing process? And how can we distill this large amount of information that fuzzers throw at us into something that is meaningful for the developers? Can we group the crashes? Can we rank them? How do we get there? What are best approaches to be used there? I do have my own opinions, but I want to hear yours. Kostya is shaking his head. Is it hopeless?
Sweat and blood. You don't have anything else. We had several war stories where we would discover a bug by fuzzing. It would be ignored. Then we would discover the same bug in the field in an expensive way. Sometimes with GUI PaySAN, which is good. It means our telemetry is working. Sometimes where white hat hackers who would just sell us the bug, and sometimes even in even worse ways. And those events trigger a reaction. Our goal is to make this reaction continue and grow further. And still sweat and blood.
So allocating more developer time to it, or what's the approach? Or do we need more tooling? Like sweat and blood is needed, right? But are we doing the right approach? If you're having 930 bugs in the queue and the queue is growing, are we missing something?
I wish I had an answer. It is usually relatively easy to keep a project from a large number of fresh bugs. If the project state is good, it is relatively easy to keep it in this state. If the project state is bad, and I don't want to point fingers, but Linux kernel and syscaller show some very scary statistics. If the project is in a bad shape, it's really, really hard to bring it into a good shape. I don't have any magic tools here.
All right. Compartmentalization could help, and then focusing on a sane component. Like many of the bugs are in some weird drivers that are somewhere far out. I do remember the static verification approach that Microsoft led to make drivers more secure, so that actually improved the code quality on the Windows kernel side quite a bit. but it's also involved a lot of blood, sweat, and tears from the developers. So Justin, what do you think?
Yeah, so I think this kind of goes back to my 20 bugs comment, right? And so unfortunately, like row harder is not really great, like actionable advice to devs stuck in this problem. I strongly agree with Kostya's insight there that like if something is bad, it's very unlikely you're going to be able to grind it out to make it better. And that was kind of what I was getting at when I was talking about when you have a large volume of bugs, like you have a fundamental quality problem. You have made it too high of a cognitive cost for teams to get something right when they're contributing, or you've made it too easy to get things wrong. And so we see this in libraries, we see this in subsystems, like you had mentioned, particular drivers or exotic less exercise things, but we also see it in like commonly used platform components. Like there's a little bit of a hotspot in the telemetry reporting APIs right now. You can go, see this if you can look at MSRC cases. And so that team made some design choices, and now everyone who consumes it has this additional cost placed on them to think about how are they going to use it safely. And so good news for us is we can kind of go dig into that one hotspot. I think the key on all of this is developer calories are the bottleneck. The best things we can do are make bugs highly actionable, make it extremely or as easy as possible to reason about the bugs and to reason about them in a deep way. A shallowly understood bug gets a shallow fix. Right. If a developer doesn't understand the bug well, they're likely to fix a symptom and not the root cause, and we're back to square one. So sanitizers are like an amazing step forward, and like in that way. The other thing that we found is there are some efficiency shortcuts. Watson uses this approach of closing things out if it stops occurring. And so when we are running future fuzz runs, if bugs no longer trigger from these regression samples that you had, we will automatically close a bug out of a queue. And so you can think of that as like automatic deduplication in a way. Obviously, we inversely will reopen it if it begins happening again, because sometimes it's just that the bug is no longer reachable due to some other change. Right. But clearing things off of a developer's queue for free, making sure that the things that they are working on reproduce immediately and are as actionable as possible, I think are the only ways we can do it. And then finally, getting out of the find fix hamster wheel of doom, where we get people to go and take more durable approaches to how you engineer the system once you've spotted a quality problem thanks to fuzzing.
Yep, that makes sense. Marcel, do you want to comment as well?
Yeah, I just wanted to follow up on Justin's comment that we should make reporting of bugs as easy as possible. Shallow reports get you shallow fixes. So if the developer doesn't understand the report, then the fix will not be very, very good either. And that's very interesting from an academic perspective, because we have been working on automated debugging for 50 years. And we've also found that industry, like we have worked on software testing for a long time and hasn't been adopted for a long time. But debugging, automated debugging, we developed these techniques, and we've been regularly looking at how industry does this debugging. And debugging has been done like it's been done 50 years ago, using printline and sort of a logging code and logging the current state and stuff like that. So very more like art than science. So but maybe now it's time to bring up these automated debugging techniques that we've developed, and kind of generate explanations of what goes wrong, because we can do that. Maybe now that we're at the point where we can automatically report 930 bugs and more, right? Not only cluster them based on the root cause of the bug, but also explain what goes wrong. And if like any two bugs have the same explanation, then you cluster them into one. And with that explanation, you can also allow the developer who is consuming the bug report to understand what goes wrong. We are also in the academic community working on automated patch generation. That's a hot topic for like the last 10 years. How do we automatically generate a patch given a bug? And it will be interesting to hear what. So I can understand if the software system is bad, automated repair doesn't really help. But maybe if there are like only a small number of bugs, how does industry stand on ideas from automatically generated bug fixes? Is that something which could be considered, particularly given that there are many systems with like maybe quickly understandable bugs, but there are no developer resources to really fix these bugs? So what's your opinion on that?
Do you trust these systems?
I was actually mentally equating it to the kind of discomfort that comes with like automated weapon systems. Is like, do we put the decision-making ability in the machine hands, or do we power assist a human by generating a candidate that a human could review and approve? I think that would be a lot more palatable, but I think everyone is buried in issues, and that leads to an open-mindedness of what approaches could actually work.
Yep. Kostya.
I'm a skeptic when it comes to automated patching. I think that such systems can do a good job in simple cases, but in those same simple cases, humans can do an equally good job at relatively low expense. In complicated cases, I wouldn't trust. Like, if you want to build a concurrency problem, if you want to fix a concurrency problem, I would rather not have it in the first place, of course. But if you do have it, I would still give it to a human, even though this human has probably introduced it in the first place.
Let's stick around with these types of bugs for a bit. I think that's an interesting topic we can drill in. When we are looking at the Linux kernel, for example, there's like a lot of complex subsystems, and a lot of the bugs happen due to interactions of these different subsystems, where the interactions are not always perfectly clear, where stuff is allocated, where stuff is freed, and this leads to like all different kinds of weird issues where bugs arise. How can we move fuzzing to, or scale fuzzing to these larger systems, and also gain some more information that we can pass on to the developers on how to actually fix the bug, or get rid of the bug in the first place, or make sure that the developer knows the necessary preconditions? Justin.
I think there's actually some interesting work going on both in Microsoft Research and in what we call the engineering systems group. Engineering systems being focused on building tools. They're taking an approach of differential tracing. So if you've heard of time travel debugging, they're leveraging that technology to trace things where an instance where the bug is observed versus not, to then quickly highlight in a developer consumable way, like what the variant is, and that they can then go and reason about it. So it doesn't attempt to reason about what the problem may be. It's just highly likely to correlate with what the developer needs to go look at to figure out what might be inducing the issue. And in that way, it can also be used to validate correctness after a fix as well, which is, at least in Windows, by far the most expensive part of a fix.
Yeah.
So I think while that specific technology isn't going to fix everything in the world, I think automating the analysis and data collection portions is, again, kind of the key insight there that will help developers spend fewer calories per bug and, in theory, like create efficiencies.
Anybody else?
Frankly, I think there is much more social problem here, problem of incentives than a technical problem. A lot of entities that work on Linux kernel are much higher incentivized by time to market, write and forget, other than long-term maintenance and quality.
Right. Or
so software engineering is about humans more so than about code.
oh, that's a very nice statement. I'll quote you on this. Yeah. You're throwing me off my line of questions here, so I have to readjust a bit. The most closest one is how can we actually help developers with that? As you're bringing up the human angle here, how can we onboard developers? Would it make sense to have first-class language support for some fuzzing primitives that go beyond writing your libfuzzer stubs, but making it part of the programming language to make it to reduce the burden for fuzzing? And how should we best approach that?
Yeah, for that I had several proposals in the past. Basically, I want a language, and this could be C++ or any other existing language. It doesn't necessarily have to be a new language, where you just put a single keyword on a function, and your toolchain knows that this is now a fuzz target. But of course, the input types has to be serializable for that. And in C++, and even worse in C, if your function has arbitrary input types, they're not as easy to serialize because pointer chasing is not solvable in C++ in general.
And everything is a char pointer, and the char pointer can become everything, right?
Of course, but well, if you follow some guidelines in C++, like if you are not using raw pointers as arrays, if you're only using containers and such, then it becomes a tractable problem, right? If your functions consume only STL containers, protobufers, or equivalent, you can still work with C++ reasonably well.
Marcel.
Yeah, so maybe I can comment on that. So so I see, as I said, I distinguish system level fuzzing and unit level fuzzing. So AFL is more of the system level fuzzing kind, and libfuzzer is more of the unit level fuzzing kind. So as KCC said, you just what he wants is point the libfuzzer to a unit and then generate test cases for that unit. Now, that is a problem that we've looked at in academia as well. Unit testing. The problem is, for instance, so there was looked at specifically for Java. You have a Java function and you want to generate objects for that function. How do you get objects that are realistic? And so an answer to that was you mine these objects by running system level inputs and then look at what goes through that function, and then kind of capture those objects, serialize them, and during fuzzing you kind of deserialize them, make them objects again, and in our case we can then modify these objects. Like libfuzzer could then take these objects and modify them slightly using mutational fuzzing. So maybe that's a way of solving that problem.
Isn't that one of
you run? Actually, KCC he mentioned something like that earlier, because you can during production essentially look at what goes through this function and then capture sample if you want inputs to that function, and then during fuzzing use these. That sounds like a solution to me.
But if I remember correctly, that was part of his wish list that he would like to have that, but it's not working yet, right? So what is stopping us from actually having this automatic system that uses feedback from live systems to learn types, interactions, and like messages that are being passed between complex systems?
Privacy is one of the biggest issues. Like if your live system deals with user inputs, it is almost impossible to do it in a way that will be compliant with the privacy goals. If you are not dealing with private sensitive data, you basically can do it today in most cases. And I think at least in one case we are already doing it.
Right. So you think you cannot? Are you saying you cannot even do this on the server side if it's touching user data, or is this more on the client side? Just for clarification.
No. Server side is technically easier because all the data is on your servers. You don't have to ship it. But if you look at legal issues, it's all the same.
Okay, fair enough. Guinea pigs, local guinea pigs. Like there's 50,000 people working at Google, right? Or likely many more now. But yeah. Justin, you had another comment.
Yeah, that's the Microsoft calls our guinea pigs self-hosters, and so there is a healthy population of those. But the thing that we've run across when trying to do this, even for API fuzzing, not for this kind of magic keyword, is that the things that are most interesting are often not exercised in production scenarios, and so waiting for samples can be limiting in that, like, you want to be finding bugs not only where the code is being exercised in like common configurations, et cetera. And then of course, you've got all of the compliance issues that come with user privacy. Back to the kind of question that primed this discussion though, I think, kind of one of the points I made at the beginning was lowering the activation costs for developers, making it as easy as possible. The Golang first-class fuzzing proposal is ridiculously exciting. I would love to see that land, be integrated, and be this kind of like shining beacon on the hill for other like standards bodies to look to and adopt. I literally forwarded that blog when it was published, or the blog, there was like a post around the fact that it had been submitted to our compiler team, and it was like, look at this, like we should be thinking about this as well. And so I'm cautiously optimistic that if that is adopted, it will kind of like lead to similar thinking and adoption by things like the C++ standards body. And we don't have to solve every problem right before we can start making a dent anywhere. And so I think, while it's really tempting to kind of geek out on some of the like things we could do today, I think it's an awesome North Star for us to be pointed at. Get it into developers' hands in the tool sets that they already work in the ways they already work, make it part of a future language standard, et cetera. Like that's going to be the same thing like we were talking about with the GitHub button. It's make it ridiculously simple, adoption will skyrocket. That's just how it works. And until it's simple, we're all going to be pushing this boulder up the same hill.
Yeah. Very well taken, this point. Very good. Marcel.
Yeah, so actually that's a good point. There is work which is called property-based fuzzing, which is similar to writing test drivers for your program, which is making it really simple for developers. You write it like a test driver, but you call it property-based fuzzing. You essentially say these are the types for your functions, and this is the assertion, and then you let the fuzzer generate inputs that try to violate these assertions. So definitely interesting to make it very simple for developers to adopt fuzzing.
Kostya.
Yeah, if we go to the kind of system level fuzzing, what we are trying to do at Google in certain parts at least, lots of our components use protobufers as the interface, and I'm not talking about a library like a single parser of something or a single small component, but a huge thing. It takes protobuf in and it produces protobuf out. We can fuzz those things automatically. It won't be libfuzzer or AFL. Those fuzzing engines don't scale to this size, but the same concept and the same approach can be used more or less automatically. And of course, it is not instead of unit style fuzzing, it's in addition to.
Mm-hmm. Justin?
Yeah, one of the other things I wanted to mention is where we can't make it ridiculously simple for developers, we've tried automating some of the hard parts. So one of the places we've had really good success here is automatically generating syscaller definitions And then in many places, that's sufficient. And so since we have, private symbols and source information, we can get pretty accurate pretty quickly. And then in the places where those definitions are insufficient or incomplete, we've asked developers and feature team maintainers to kind of like keep them current or refine them further. So sometimes you just have an opaque void pointer on a boundary, and getting teams to kind of enlighten what the actual structure that it will be when it's interpreted, maybe associating that with a particular enum that it's going to be cast based on, et cetera. And that has actually then made it so, in a situation in a team like ours, we can have centralized infrastructure. We can ensure that we are automatically generating and bootstrapping everybody to a minimum standard of quality. And then each team just has to worry about their own little slice of the world and keeping up their coverage and their definitions current with their work. And then we're able to then push out and do highly local fuzzing. So we can fuzz feature teams' features on their branches, and we can pay special attention and dig deeper and focus things like syscaller only hitting certain families of APIs, et cetera, to make sure that they're getting like the most calories out of their fuzzing cycles that are happening for their features and their branches. So it's not exactly free, but it means they don't have to understand a lot of the basic principles. We can kind of like teach them how to refine versus having to start from scratch for the hundreds of teams that we have to deal with.
So both you and Kostya now answered part of my next question or my next topic, but I want to answer or ask the question any way to get maybe a more complete answer. Like Justin, you mentioned API descriptions, a little bit of structure. Kostya, you mentioned protobufs and others. And especially when I think about large complex software systems, and I just pick Chrome, for example, with many different libraries, many different components, communicating processes, compartments, and so on. How do you fuzz such a beast? Does it even make sense to fuzz it end to end? How do you keep track of like general properties across the whole stack of intercommunicating sub-processes and different components? Like, yes, sure, you can run unit tests on one component, but how can you do it? How can you run a large chain of these parts?
I can jump in there.
Go ahead.
Yeah, we use emulation. We do full system emulation. It's the only way that we have found to kind of like tractably solve that problem.
Snapshotting or?
We do leverage snapshotting. We get it actually. I'm going to come back to the efficiency of snapshotting and why we like snapshotting. But when you think about Windows and the way Windows is built with COM and RPC, kind of like silently creating all this like weakly bound plumbing all over the operating system, it was very difficult for even the developers to reason about all the things that might be exercised with a particular piece of functionality. For example, when you are just trying to make a web request, you use a WinHTTP client that actually goes and silently starts a service and initiates a COM call. And so like a consumer of that library might have no idea that they're going to be exercising some secondary service, nor should they have to. So instead what we do is we capture the whole OS in an emulator. We do pay about 100x cost for the emulator in terms of like execution cost. And that's a big part of that is because of the instrumentation that we have, in addition to just like the pure, like cost of doing business in an emulator. But when we then use snapshot-based fuzzing and the 100% repro that comes from using emulation, we get roughly the same throughput and roughly the same number of fixes versus using native. I actually think our fix rate is way up since using emulation because every prog repros 100% all the time. But yeah, using snapshot fuzzing, it means that if you were to blue screen and need to reboot, you don't have to pay the cost to generate a mini dump. You don't have to reboot your VM or whatever other environment you're in. And so net, we actually end up with higher iterations per second because of all the elimination of all the overhead. So I don't know that applies super well to most other people's problems, but finding a way to capture and virtualize the entire environment and simultaneously instrument the entire environment and get the entire environment to execute in lockstep was the only way we found to get that repro that we need to hit our own bar for when we would submit bugs to teams.
Yep. And there may even be an opportunity to lower that emulation cost. Like if you want to fuzz multiple systems, or you mentioned, I think, 440 different versions of Windows being built nightly, and then fuzzing all of them in parallel, you may not have to pay the price for all of them. When we looked at USB drivers and fuzzing USB drivers, we hooked a virtual USB device through QEMU and fuzzed all the different layers of the Linux stack. And on Linux, we actually had coverage feedback. But then we used the seeds that were created on the Linux host for cross-pollination on Windows and Mac OS as well, and actually found a whole bunch of bugs. I think the Windows bugs are fixed, the Mac OS bugs are still open. So it's a nice way to like cover areas where you don't necessarily have coverage information out there. So it's
Sorry, and it also gets you instrumentation in places that would otherwise be almost impossible. So our virtualization team, loves it because they can get code coverage feedback from the hypervisor itself. So we can actually emulate a guest inside of a host, and collecting that coverage or performing something like a sanitizer without emulation is also kind of exceptionally difficult, and you'd end up with this very bespoke technology just for that problem. And now we're back in the realm of hacker fuzzing and developer fuzzing, and we've kind of unwound the whole point of the procedure.
Right, very nice. Kostya, do you want to comment as well?
Well, you mentioned Chrome as one of the full systems, and I think Chrome is actually more complicated with this respect than an operating system, because an operating system has a well-defined API. Chrome has a number of well-defined APIs, but they are actually much broader. And so I'm aware of very good work by my colleague Ned Williamson, who was fuzzing the browser process of Chrome, which communicates with the render via it's not protobufers, but this is something like protobufers. I believe it's called Mojo, like another serialization layer. And you can treat the browser process of Chrome as something that talks this serialization layer, and then problem is basically reduced to structure-aware fuzzing of this specific data format. But this only covers one part of the Chrome, and other parts will behave in different ways. And so I have no answer that will fit all the parts of Chrome here. Yeah.
And it's hard to keep track. So that's a nice open challenge that maybe we academics have to look at a bit more. How can we keep some, or even infer general properties that hold across all these components? Let's change gears a bit. I want to talk a bit about coverage and different kind of metrics as feedback. Kostya mentioned this during his talk as one of the open problems, moving past coverage. So far, we've been mostly using coverage, and as Marcel mentioned in his talk, it's a nice way to get insight into the program without having to pay a massive amount of cost. So you get a lot of executions per second, there's very cheap instrumentation, and you get to select a little bit based on that. What kind of, how can should we increase the precision? What are the limitations of these coverage operations? And where should we move next? And also, maybe in a more general form, one of the asked questions was what kind of useful metrics can we monitor during the fuzzing process? Right now, we look at coverage and density of bitmaps, and then we decide now it's good enough, right? We've run out of cycles. What else can we look at? Marcel, do you want to go first this time? Yeah.
Just a little bit of history about coverage and fault finding in software engineering academia. Coverage. So what's the correlation between coverage and fault finding? And there's contradicting evidence. And the current standpoint in academia is that for test suites that are manually generated, coverage doesn't seem to be correlated with fault finding. So you have a a test suite that has a little bit higher coverage than another test suite, it might not be better than the other test suite and finding errors. But this might be different for fuzzers which generate these test suites. So the key idea behind coverage and fault finding is if you do not cover a certain statement that could be buggy, then you can't find that bug in that statement, right? So you must increase coverage because otherwise you don't find these bugs in these statements that are buggy. So now coming to fuzzing and coverage. Coverage is a good signal. So we don't yet know whether if you increase coverage for using fuzzing, you also find more bugs. And my intuition is you will find more bugs as you increase coverage. Not necessarily from 99% to 100%, but definitely from 60% to 70% or something like that. So then the question is, what kind of other coverage feedback can we have, not just code coverage? And I think libfuzzer has a lot of good answers to that. So they have, maybe KCC can elaborate on that, but they have value profiles, and there's a data flow sanitizer, some data flow feedback. So yeah, KCC, do you have anything to add? I think there's a lot of feedback that we can add to fuzzers.
Yeah, so program execution is basically control flow plus data flow. And code coverage is the cheapest to collect metric of control flow. We can collect more metrics, bounded path coverage, full path coverage. Those metrics get very expensive and very non-linear, which is why nobody's using them. And which is why maybe if we use different strategies for corpus expansion, so instead of maximizing total coverage, which we cannot do if the coverage is exponential in nature, to maximizing the distance of coverage, maybe we can use those exponential metrics of control flow. Now, data flow is probably actually even more interesting. Our traditional example is, what if your program has a single basic block? Is it covered by a single test? Of course, no. Right. So you need data flow, and the way to reduce data flow to control flow, like Love and Tell paper and libfuzzer's value profile, is just a very, very small attempt to do it. We need more ways to get metric from data flow, and I don't know how to do it in a linear way. Like, I don't know how to reduce data flow to a bit set, and so we need to use data flow that is non-linear, exponential, in a way that will not explode the process.
So this data flow question is interesting. Our intuition was as well that data flow brings us a lot of additional paths that we would otherwise not see. So a PhD student spent 1.5 years developing a data flow fuzzer. We started evaluating this on a large corpus, and then we discovered that the data flow in any case that we measured was a subset of the control flow. So the control flow that from a decently optimized fuzzer was always better due to the lower cost of collecting these profiles compared to the data flow cost. There was a very nice negative result that we spent quite a bit of time that we, unfortunately, it's academia, you only publish positive results, right? That we weren't able to publish, but it's maybe we were not doing the right data flow coverage, but we were having a very hard time figuring out what to look at and getting an additional edge over just coverage-based code coverage. So I wonder, do you have any data on that, Kostya, like where this would work out, or is it more an intuition that you think it would be useful?
Yeah, it's mostly intuition. We have the data suggesting that value profiles in libfuzzer are useful at large scale, and if you take any given amount of time a leap fuzzer without value profile will behave better than the leap fuzzer with value profile. But when the fuzz target saturates, when we stop finding bugs, then value profile kicks in. So it's not
Right.
it's not control flow versus data flow. It's data flow when control flow ran out of juice.
Yep, and I think that's pretty much what we're hoping for as well. But the question is how to balance these different parts. We only have a couple of minutes left for our scheduled time, and I want to give us a couple of minutes for some closing statements, and maybe we can talk about the last big topic we aimed at. That fuzzing is only the beginning, right? Where can we move past? How can we move past different classes of bugs, and what will the future bring? So I can give each of you a minute for a closing statement and your big vision. Where do we move next? Do we improve fuzzing? Do we move past fuzzing? What else should we do? Who wants to start?
I can start.
Justin, let's do it backwards. Yeah, Justin.
Okay. So I want to leave time for closing statements, definitely, but I also wanted to chime in on the coverage. So as succinctly as possible, one of the things we have found is obviously code coverage as measuring the topology is just incomplete, right? Doesn't sufficiently represent the total state space that you might want to explore. One of the techniques that we found, while it is not particularly efficient, is adding dimensions of coverage where someone can represent the program state that needs to be explored. So a concrete example, in a TLS implementation, we added the state value in the state machine as a dimension. And so you only counted topological coverage if you had seen it in that state. And you got that same great gray box drilling behavior where our fuzzer, without any enlightenment about TLS, navigated the TLS state diagram, and we were able to automatically extract the implementation's actual possible state edges. And we're able to then compare that with the intended and actually use that to identify a different set of bugs that we were certain inputs and certain sequences were able to get us to violate the intended design of the state machine itself. So I think that there's a ton of opportunity in addition to data flow, also with kind of letting developers encode invariants or encode things like state that should be these additional dimensions. As far as what's next, I'll just hit the same theme as before. What's next really is just working in safer tools and safer languages, safer libraries. I think making fuzzing better, faster, more efficient is a noble goal, and I'm glad a ton of people around the world are interested in working on it. But our challenge right now is not, as a community, as an industry, is not supply of bugs. Right. What we need is for people to have fewer bugs to find, and we need people to be able to fix them faster when they do come up. So I think I'll leave it to people far smarter than me to think about how do we make sure that there's a bottomless well of automatically discovered bugs, and instead encourage everybody to be thinking about how do we make sure that bugs just don't exist to begin with.
Well, most bugs seem to be in newly added code, so maybe we should just not add more code.
Dude, let's all just stop writing code right now. I would love it if we could get the world to just start writing in memory-safe languages, and then think. I would love for us to be talking in a couple of years about how we need to write logic SAN, because the only bugs left for us are logic issues.
That would be amazing. Strongly agreed. Thank you very much, Justin. Kostya.
Yeah, one of my major topics is hardware accelerated runtime checks. It is the same what Justin just told, just from a different perspective. We need safer languages, and Rust without unsafe keyword is one way to get there, possible. Another way to get there is to make our existing programming languages safer, and for that, the only real avenue I can see is help from hardware. We are getting something. Our memory tagging is the best example of that. And yes, once we get rid of the memory safety and similar issues, we'll still get all the resource exhaustion, like infinite loops, timeouts, memory consumption, etc., and logical bugs. So we'll get back to fuzzing once everything is either Rust or memory safe C++.
Right. And we'll never be out of a job. There will always be different kind of issues. Thank you, Kostya. Marcel.
Yeah, definitely echoing Justin's and Kostya's words. And yeah, I also think fuzzing is not going to go away anytime soon. And I also think that we need a lot of more tooling around fuzzing after finding bugs. What do we do? How do we help developers? I also think that echoing Kostya's point and also echoing Justin's point, we need to have mitigation strategies that allow us to kind of close down entire classes of bugs, maybe at the hardware level and maybe at the software level. So, but without much performance overhead. So I love this GWP ASAN initiative. In production, you can find bugs without much overhead. And so there's a lot of new, interesting stuff coming up, and yeah, really excited.
Awesome. Thank you, Marcel. Thank you, Kostya. Thank you, Justin. Thanks all for the great discussion. I think we learned a lot about fuzzing. This was super cool. I definitely learned a lot. I hope we can repeat this discussion in real life soon with a beer and in the same time zone, which would make this also much nicer. Thanks everybody for listening. It was fun having you, and see you folks around for the next session. Thank you, everyone. Bye-bye.
Thanks for having us.